Welcome, everyone. Today is our usual Wednesday ITMP seminar. And today we welcome our guest, Mark Hertzberg from the Tufts University, who will speak about the unitarity, causality, and the implications for testing general relativity. Mark?
Okay. All right. Thank you very much for this invitation to speak here. Yeah, so I'm going to talk about some these two papers that I worked on with these PhD students. And so, yeah, the outline of my talk is begin with some motivation from gravitational wave observatories with regards to thinking about corrections to general relativity. And then I'll mention what is, in some sense, a kind of minimal approach to corrections, which is just adding curvature corrections. So it's kind of pure gravity in a way. And we'll talk about some sort of theoretical and observational problems that occur if one just sticks to pure gravity. And then in the second part of the talk will be on, in some sense, a more quote unquote optimal approach, where one goes beyond pure gravity and introduces something new, in particular a scalar field, and how consistency with certain principles suggests corrections that can show up in regimes of high densities, and some constraints on these things. And that's something we may look for. Okay, so, as you all know, we have these very nice observations of gravitational waves now from merging black holes in the case of LIGO, Virgo observatories. And so far, the gravitational wave signal is compatible with general relativity. But many people have thought about, can we use this to test general relativity and search for possible deviations? And the feeling is that because they're black holes, that one is probing the strong gravity regime. And so if we enter the very strong gravity regime, one could wonder, are there corrections? Now that's fine to say that. On the other hand, it's not clear as to what is the alternative theory that one is comparing to. So it is important to provide frameworks, theoretical frameworks that would describe corrections to general relativity that might aid in searching for possible deviations. So there's been some work, and I'll mention some work that others have done on thinking about possible ways that you might deviate from general relativity in a well-defined framework, but the various problems that go into it at the same time. Okay, so the first is a kind of minimal approach to think about deviations from GR, general relativity. Okay, so what do I mean by this? Okay, so minimal, in my language, minimal means no new degrees of freedom. Okay, so that is to say that if we can think of gravity, standard general relativity, as just a theory of 2 degrees of freedom, right? The 2 polarizations of gravitational waves, or the 2 polarizations of the graviton, the degrees of freedom that exist within standard general relativity. And so minimal would be to only have these 2 degrees of freedom. Okay, and then we'll go beyond that later in the talk. And if you only stick to the 2 degrees of freedom of the graviton, it's very restrictive already what the action of nature should be. And so first we can just look at the first 2 terms here. So this is just a standard action, d4x, square root of the minus the determinant. And these 2 terms here just summarize the Einstein-Hilbert action. So lambda would be the cosmological constant, which is not going to play much of a role in this talk because I'm interested in black hole mergers, for which, as far as we know, the cosmological constant or possibly the dark energy is irrelevant, but I just include it there. for completeness. And then this is the Ricci scalar. And kappa here is proportional to the square root of g Newton. Okay, it's the gravitational coupling. Okay, and so this is just the Einstein-Hilbert term, and this is a cosmodrome constant. And if we say that the action should stop at two derivatives, this is the end of the game. It's just these first two terms. I don't know, can people see my cursor, by the way? My mouse?
Yes.
Yeah, okay. So this is a zero derivative term, and this is a two derivative term. And so if you stop at two derivatives, that's all you can write down. So from this point of view, general relativity is kind of the unique theory at two derivatives of these two polarizations of a spin 2 particle, of massless spin 2. Okay, so that's that. Now, of course, I should add the coupling to matter. I haven't included that here, but we've standard coupling to matter. Here, I'm just writing down the gravitational part of the action. Okay.
Do you put any constraints on the equations of motion, like, the absence of ghosts, or you just write as general action as possible?
Yeah, good question. So at this stage, where this will be a general action, and here when I say no new degrees of freedom, I'll impose only from the perspective of low energies. Because yeah, so as long as those new, as the new corrections that I'm coming to in a second will inevitably have new degrees of freedom, okay, if I take the action seriously, even though I'm in a minimal approach where I said no new degrees of freedom. And so what we'll have to do is take this action as written only seriously at low energies. So the new terms that come in will introduce new degrees of freedom, which will include ghosts. But as long as the mass of those new degrees of freedom is high in some sense, we will not consider them to be part of the low energy theory. So from a very low energy point of view, we have this, and there aren't formally any new degrees of freedom. There are formally new degrees of freedom, but we don't trust the theory when those degrees of freedom become active. Does that answer your question?
Thanks. Yes.
Yeah. Okay, but just to clarify for any non-experts, these first two terms is just standard, would be standard gravity. Okay, where lambda we may be zero or non-zero, we don't know, probably non-zero. And then going beyond general relativity would be to add higher order terms. Okay, and so I have a very simplified notation here. When I write R2, this will be something quadratic in R. Really, I mean something quadratic in the Riemann tensor. Okay, so something like, yeah, Riemann contracted with Riemann, things like that is what I mean by R2. And then when I write R3, that can be three contractions of Riemann. Okay, Riemann is a four-index object, so there's multiple ways you can contract its indices. It turns out to be two relevant ways for this discussion, and so on. I'm not going to talk too much about corrections that do not involve, in fact, really, I will only talk about corrections involving Riemann. So even though I wrote the letter R there, I do mean Riemann, contracted with Riemann. And that's because we'll primarily be interested in, say, at least for the first half of the talk, people have been very interested in merging black holes that are Kerr black holes. So Kerr black holes are vacuum solutions of the Einstein equations. And in the vacuum, the Ricci scalar is zero. And the Ricci tensor, R mu is also zero, at least if you, for chargeless neutral black holes. And so the thing that really matters are corrections that involve Riemann, because Riemann is non-zero even in the vacuum if you have any sources around. Okay, so that's why people mostly focus here on Riemann. And Riemann is just honest to goodness gravitational correction. Okay, so what I'm doing here, some of you may know that some people write down something called f of r, where they write down powers of r, Ricci. And this is known to just be equivalent to turning on a scalar. And so at least in the first half of my talk, that's not what I'm doing. I think of it as pure gravity with honest to goodness gravitational corrections that cannot be mimicked by a scalar or anything. That's why it's Riemann. So anyway, there's an expansion that I can write down like this. So quadratic, cubic, and then quartic corrections plus ... And when I write this down, one have in mind, or at least many of us have in mind, I have in mind at least, that nature probably has these terms out there at some level, even though we've yet to detect any of them. Because at least most of us think of general relativity as just an effective theory that's only valid at large distances. And the scale at which it breaks down is not known. It should break down at least certainly by the Planck length, but it's conceivable that it breaks down on a scale significantly bigger than that as well. So from that point of view, one should, if you have any old random effective field theory, in principle, you should just write down all possible operators, some tower of operators, and like I've indicated here. Okay, so people have taken these kinds of actions. So I highlight a paper here, for example, from 2019, where they said, well, suppose these corrections are there, and these corrections have these coefficients. So I call it alpha 3 and alpha 4 and so on. And these coefficients, the cubic coefficient alpha 3 and the quartic coefficient alpha 4, if I make their units manifest, turns out, okay, alpha 3 has units of 1 over mass to the 4, lambda has units of mass or length to the 4, alpha 4 has units of 1 over mass to the 6 or length to the 6. And if you add these corrections to Einstein gravity, it's quite a bit of work, but you can then start to recompute what would be the gravitational wave signal from merging black holes. And since the data from LIGO Virgo is compatible with general relativity, that just puts an upper bound on the size of these alphas. They cannot be too big or we would have seen corrections. And they get a bound that if you translate it into a length scale, lambda to the -1, is less than something like 150 kilometers. Okay, that's the bound. Okay, so this number, 150 kilometers, is not too shocking because, like, if you think about the first LIGO merger, it involved two black holes, each had a mass of about 30 solar masses. And so they have a Schwarzschild radius of around about 100 kilometers. Okay, so if you're probing things whose intrinsic scale is order 100 kilometers, and your data is good but not great, you don't have really high precision because this is just early detections of gravitational waves, right? Gravitational waves are so weak, we don't detect them with incredible precision. You can figure, ballpark, you should imagine that the bounds on the length scales that appear in this expansion should be order 100 kilometers. Okay, well, that's what this number is, in fact. But they had to do it, they didn't just do order of magnitude. This is some real calculation that reveals this particular number. If you want to convert that to particle physics units, it's something like 10 to the minus 12 eV, a disturbingly low energy scale, but that's what it is. Okay, so
I guess you are using that the quadratic term is total derivative, so it's not relevant actually.
Yeah, thank you for this question. I skipped that point. That's right. The quadratic term, does not affect the classical equations of motion, as you know, because if I have Riemann, I can, if I want, write it in terms of Gauss-Bonnet term plus Ricci squared, R mu nu squared. And the Gauss-Bonnet is a total derivative, so it doesn't affect the classical equations of motion. And as I said, R and R mu nu both vanish in the vacuum anyhow. So the quadratic term doesn't affect the equations of motion. So the leading bounds actually, the interesting stuff actually comes from skipping beyond the quadratic to cubic and quartic. And they actually focus their attention on the quartic term, funnily enough. And that's related to something I'll come to shortly. But there are reasons why the quartic term needs to be somewhat large relative to the cubic term due to some interesting bounds related to causality. But essentially, this is more or less the same bound for the cubic term as well. You just have to be a little careful. So roughly lambda 4 and lambda 3 are both bounded to be length scales less than about 150 kilometers from this analysis.
Can I ask a question?
Yeah.
Does this bound, this LIGO Virgo bound, go well with millimeter or submillimeter test of Newton gravity? because or it has nothing to do with that?
Yeah, this is a really good question. So this bound here, okay, so let's say lambda 4 is close to this number, okay, or
Yes.
just yeah. So then you put that back into the action. Let's say that is the action of nature where lambda is say 100 kilometers or something. So if you then take this action and study it as just a classical field theory, it turns out that the corrections to, like, I guess you're talking about like tabletop tests of gravity, those are unaffected, even though you're probing down to like 30 micrometers, something like this. And the reason it's unaffected is just because the value of Riemann if you have like two lead balls or something and you look at the attraction, the value of Riemann is so fantastically tiny that it doesn't actually matter that you're in our minds probing a length scale smaller than this thing. Now, it may matter in a sense. It's one of the important points of the talk is that it matters to a theorist. A theorist is a bit disturbed by a theory that has this kind of low value that suppresses the higher order operators. But let's say you put aside that issue for a moment and just treat it as a classical action. It's not ruled out by laboratory tests or even solar system tests, just because Riemann is so tiny in the lab and the solar system. So these authors were correct in that the most precise bound does come from.
Excuse me, can I also ask a quick question? Does this mean that we cannot use this action at scales, at energy scales above 10 to the minus 12 electron volts, at least for gravity?
From the point of view of fundamental physics, it seems the answer is no. So in this paper, so I'll comment on this in a slightly more precise statement associated with that in a minute. But basically, that is true. I have to clarify why that's true. It's a little bit subtle. But these authors also, these are clever people, they also suspected that from a particle physics point of view, this seems very unsatisfactory to have such a low, what looks like a low quote-unquote cutoff on the theory. So they say words like, well, maybe there's a UV completion that is a soft, quote unquote, UV completion that prevents us from noticing anything peculiar at lower scales. So in the work that I'll describe shortly, that doesn't seem very plausible. But you're asking the question, which was kind of the question that we had, as to how seriously can you take such a theory with this kind of value of lambda? Okay. Now, I should add that well, I even have that commented here. We've tested gravity down to 30 micrometers. One thing we could note is that if you were to think about the unitarity cutoff on this theory by scattering, say, a pair of gravitons off of each other, and let's say you use this Riemann to the 4 term, so it's even tree level graviton scattering, the cutoff on that is not 10 to the minus 12 eV. Because when you do that calculation, there'll be additional factors of M Planck that come into play, right? Because you can write Riemann as something involving leading order involves 2 derivatives of the gravitational field, but then it's canonically normalized by a 1 over M Planck. So 2 to 2 graviton scattering violates unitarity. I forget the number, but it's at many orders of magnitude bigger than this because of the M Plancks that emerge. So said differently, this number, 150 kilometers, is purely a property of the classical field theory. Unitarity bounds should involve some h bar. So it's parametrically, it turns out to be at a different scale. But it turns out that does not really save the theory to high scales, nevertheless. Okay, so let me try to address whether we should trust, on what scale should we trust this theory? Let's say a bit more. So what we thought about in this first paper was that we wondered if you're going to have such relatively huge corrections because the length scale here is so big, what would happen if you try to obtain those corrections from some simpler construction, say at a more conventional 2 derivative action? Okay, so maybe we thought this could help to shed light on this issue. Okay, so imagine, just for the sake of argument, that there's a bunch of decoupled massive scalars out there. Okay, so I labeled them I. They have some kinetic term and some mass term, and then the regular matter. And let's imagine that they're completely decoupled. So it's not, we would not have directly seen these things in the lab. I'm not coupling them directly to matter, but of course they talk to gravity. Well, even if you do this, and these particles have a mass, you can integrate out these particles. And because they talk to gravity, when you integrate them out, you generate higher order curvature corrections. For example, these authors had done this in 2021. So the alpha 3 and the alpha 4 that I was just mentioning a minute ago have these formulas. Okay, so naturally, if you make the mass of these particles very heavy, when you integrate them out, you get very tiny corrections. So the mass appears in the denominator here and here. And then there's these kappa squared, as I said, is just basically G Newton. Okay, so you can generate this from a standard looking action. And then you can ask further questions as to what happens as you push the parameters around, like M, and the sum is over the number of species. Okay, so in some sense you have two parameters, the masses and the number of species. And naively, you can think of M as the acting, let's say all the masses are the same or similar for simplicity. You can think of the mass of the new particles here that you're integrating out as acting as effectively the real cutoff on the theory. You cannot possibly trust the low energy theory, which is this thing, which has no scalars in it, at energies above the mass of the particle, or at length scales smaller than the Compton wavelength of M. So M is acting like the cutoff. But you might imagine that the values of the coefficients that I called alpha here, naively could still be very big. Naively, they could be big because you could imagine there's a humongous number of species. So you could say, I'm integrating out relatively heavy particles M, so that makes the couplings tiny. But I sum over a gigantic number of them, so that makes the couplings big. And I could make the coupling up as big as this if I wanted to. So that's a naive thing to say. But I mention that because it tells you that this number here is not trivially connected to the cutoff on the theory, because maybe M is even much bigger than 10 to the minus 12 eV. And the reason lambda is down to 10 to the minus 12 is because you summed over a huge number of particles. But it turns out that causality says, from this work, says you cannot do this. These higher derivative operators can lead to superluminality. So there are bounds that come from causality, which says you cannot make that true. So in fact, there's a bound that says basically lambda 4 and lambda 3 are bounded to be an order 1 number, 1.4 times the mass of the lightest particle in this sum. So I'm not allowed to make the mass very big whilst keeping lambda that small number. So this is a long way of saying something that most people may have guessed. If you're a particle theorist and you see that I told you lambda is, say, this number, you would say that's the cutoff. But I just emphasized to you that's too quick to conclude that, because there are M Plancks. That's not the standard unitarity cutoff. But from the point of view of causality, it plays the role of the cutoff, nevertheless. So it's somehow causality is sharper than unitarity in this context. So playing the game of summing over a huge number of particles helps, but is not enough. You still have this inequality. So therefore, if you want lambda to be tiny, like 10 to the minus 12 eV, the particles at best, they can have a mass that's also 10 to the minus 12 eV that you're integrating out. Okay, but again, the M Plancks don't help. Is that clear to everyone? Okay, so the punchline therefore is causality demands that these new particles have to indeed also be very light. Okay, so they have to also be down to 10 to the minus 12 eV. So those are the mass of the particles one is integrating out.
Can I just clarifying question? It's a causality bound or the bound based on superluminality, because it's not always clear if superluminality implies violation of causality.
I think these are in a context in which the interactions like in this theory, let's ignore lambda for the moment.
Mm-hmm.
Let's say lambda 0. So we can have some localized sources, and then everything falls off towards 0 sufficiently quickly that we have asymptotic Minkowski space. And so then the superluminality really means that if you have this localized source, it kind of just looks like, I don't know, like a black box where something is traveling faster than c, and then everything asymptotes to c again asymptotically. And so in this situation, I think this faster than c in this context is unavoidable in terms of tension with causality. I think you can avoid these conclusions in other contexts, like if you do not asymptotically go to Minkowski quickly enough and so on and so forth, then it's rather more subtle and less clear. Or if the deviations from superluminality from C are sufficient, parametrically tiny, but I don't think that's true in this context. In this work, they rigorously prove that you break some of the analyticity bounds as well.
Oh, okay. Okay.
So, yeah, I call it causality, but you could say analyticity if you prefer those.
Yeah. Mm-hmm. Thanks.
Okay. So all right. So here's a theory where the mass you're integrating out is 10 to the minus 12 eV, and you generate an effect that's on the edge of detecting by LIGO through a loop effect. Okay, you get these Riemann corrections. On the other hand, if I go back to this action, okay, this action looks pretty nice. Because if I say, well, that was the action I had all along, it does not look too bad. And yet secretly through quantum mechanics, this thing could affect LIGO through higher order Riemann curvature corrections. So it's what looks like a boring theory on one hand is an interesting theory at loop level from this point of view. So so far I kind of summarized some other people's work. So what would we really add to this? What we were thinking about was, okay, if this is the action that generates these Riemann curvature corrections, and I might add, by the way, so they're interested in this action. Who's to say where the action comes from? And at least from my point of view, I do not know many ways of generating large corrections other than through integrating out heavy particles. I'm not saying that's literally the only possibility, but I think you agree there aren't many possibilities. And maybe you could try large extra dimensions or something, but that's not what I'm going to discuss here. This is just from integrating out particles. So this is fairly general, I would argue. Of course, these particles don't have to be spinless, but it doesn't change much if you give them a spin anyhow. So it is moderately general analysis. Okay, so what we thought about was if this is...
Sorry, just a question, just for completeness.
Yeah.
So in principle, you can have a setup like in string theory. You have three-level corrections. You have exchanges of heavy particles between gravitons.
Mm-hmm.
That induces higher curvature correction, right? Just alpha prime expansion in string theory.
Right, but corrections...
This will not be loops. This will be just three-level exchanges of towers of all states.
Yeah, well, I suspect that's closely connected to extra dimensions, though, is it not? Is it like a tower of Kaluza-Klein modes?
No. In fact, the unitarity and causality, the coefficients will be consistent with basic principles.
No, I'm not saying it's inconsistent, but if my starting action is just a four-dimensional action of particles, there's not too many options. Or if I, let's say an action for particles, I either have extra dimensions or I integrate out heavy particles. But you're right, if I have strings or something living in higher dimensions, you think you can do this thing you're referring to in 4 dimensions?
Yeah, I don't think there is a big difference. Well, there could be, well, you need probably to consider superstring, then the leading correction is like R4,
Yeah.
there'll be no RQ.
Yeah.
But otherwise, it's conceptually, it's just that. You need to have you need to have infinite number of
Right. Yeah.
That's true.
Yeah, so, if we view these as alpha prime corrections, of course, we'd have to check the numbers, but presumably we're then having an alpha prime, I'm guessing that's something connected to this scale. So one would then have to check the various consequences of having such a gigantic alpha prime or the square root of alpha prime, I guess, is a length. So a string length that's 100 kilometers. We can imagine all sorts of problems that might happen if we do that. But what you're mentioning is something interesting to think about. So thank you. Okay. In the context of integrating out heavy particles to loops, we wondered, are there other related problems that occur? Because if you accept this action, okay, you do get corrections at order 150 kilometers in terms of Riemann curvature corrections. Or we can get it down to 100 kilometers or 10 kilometers or whatever you might need in order to keep testing gravity with finer and finer precision. But are there other maybe unintended consequences of doing this? So this is also a loop correction, but it has a slightly different consequence, as I'll describe. So let's say you just have some regular matter here, two objects, and you have some one of these particles running in a loop. Okay, so this might be the Earth and the Moon, whatever it is. Okay, and then you have a scalar particle in a loop, and then you sum over all the particles. You can compute the one loop correction even when the exterior particles are, say, moving slowly, for example, compared to the speed of light. You can look at corrections to the Newton potential. And at one loop, there are these diagrams. There's also corrections from the graviton running in the loop, but we're going to sum over n particles where n is big. So the corrections from the scalars will dominate because there are so many of them. So anyway, it's this kind of obvious pair of diagrams at one loop, the scalar, graviton, vertex here and here. To do the renormalization correctly, it's a fun little exercise where to cancel all divergences, you also need to renormalize the Newton constant. That cancels one divergence. That's represented by this diagram. And you also need to renormalize the cosmodrome constant. So even though you might take the renormalized cosmodrome constant to be more or less zero, you do need to shift it from its bare value to cancel another divergence. And then everything is finite. Okay. And it's a fun little thing. The scattering amplitude, so two massive particles come in, two particles go out. One loop has this slightly ugly looking amplitude, but there it is. This is just a tree level one over q squared, whose Fourier transform is 1 over r. That's the usual Newton potential if you do a Fourier transform. And then there's this correction from these particles running in a loop. It does not have a neat analytical form because you have to Fourier transform this thing. Nevertheless, you can numerically compute it. And so, yes, it's a correction to the Newton potential. And if you operate in a limit where the distance between the two objects is a little bigger than 1 over m, the mass of these objects, it takes on this asymptotic form. It starts to look more like an exponential. It has an exponential fall off. That's not surprising because you have a massive particle in a loop, so you should expect its corrections to be irrelevant at large distances. So indeed, at large distances, if you made r much bigger than 1 over m or 1 over 2m, these loop corrections here are not doing anything new, and the whole effective field theory collapses to the thing I promised you, which is this thing. There are other diagrams that generate the Riemann corrections. Okay, so at large r, there's no inconsistency here. Formally, the low energy effective field theory is just the thing with Riemann corrections. Okay, because this is exponentially suppressed, this new thing that I'm referring to, or this other thing that I'm referring to. But then one has to check, are we really in the asymptotically large R regime? Okay, because the m here, we said, couldn't be much different than 10 to the minus 12 eV. Precisely the scale, roughly the scale we're probing. So now there's some tension, because we're not actually able to go much beyond this asymptotic regime, where it's just an EFT of operators in powers of R. We're really seeing these kind of corrections that aren't that suppressed. So we're really in a regime where the exponent here is order 1, not where it's like order e to the minus 100 or something. So anyway, this is a little bit different than the common parameterization in the literature. So in the literature, people like to write, well, some people like to write corrections to the Newton potential, minus g m1, m2 over r, as 1, and then the correction is some prefactor alpha. Unfortunately, there's too many alphas in this talk. There's not the same alpha as before. E to the minus r over lambda. So you can see here that lambda is 1 over 2m. Okay. And so it's not quite this, because this also has a 1 over r to the 5 halves, so it's not quite 1 over r. But it falls off pretty, this is a pretty slowly varying prefactor compared to this. So you can kind of put it into this form if you take alpha, sort of uplift it to be a moderately slowly varying function of r. Okay, if you do that, you can compare to the known solar system bounds. Okay, so if you start affecting the potential, say between the Earth and the Moon, or between the Earth and the Sun, and all sorts of things, you will you can look for that in various tests in the lab and in the solar system. Okay, but this is some loop effect. Okay, so it's not the classical action as we discussed earlier, which does not have corrections in the lab. There's a loop effect which does have corrections. And anyway, so these are various, the yellow is various known bounds. Okay, this is the value of alpha on this axis, and this is the lambda. And remember, lambda is just 1 over 2m. Okay, so heavier particles down here, lighter particles are over here, of the particles we integrate out. And if you push the lambda 4 that we talked about to be 1 over 150 kilometers, like I said here, that pretty much determines everything. You have no freedom if you want to have this size of an effect. So these scalars are doing two things at once. They have this loop effect, which has this formula, and there's the related loops that are generating Riemann corrections, and they have to be at this level to have any chance of seeing them with LIGO with current data. And so then you can actually predict a relationship between this loop effect alpha and this other mass m. And so you get this line here, a very steep curve. Okay. So you need to be in the regime where it's allowed by solar system data, which is in the white region, but not ruled out in the yellow region. And so there's a bit of a problem here, right? Because LIGO, remember, is testing down to about 150 kilometers. Okay. So if you look at where 100 kilometers is also, that's like here, that's 10 to the 5 meters, 100 kilometers. So if you follow that curve up, it's way up here. It's on the blue curve up in the forbidden region, or ruled out region. So curiously, by adding these operators that give corrections that's on the edge of LIGO discovering them, this particular kind of sort of UV completion in terms of integrating out massive particles has an unexpected consequence, which is that it has a corrections at the solar system through a loop effect. So this is a bit interesting, perhaps. At least interesting enough for us to want to write a paper about these points. Can you imagine a regime where you're not ruled out by the solar system? Well, you can. You just have to keep changing the lambda 4. So if you make lambda 4 this number, so go down from 150 kilometers down to 8 kilometers or so, then you suppress the higher order Riemann curvature corrections because they're suppressed by like this lambda to the 6. Okay, so they're much suppressed. And that moves the blue curve down to this orange curve. And I've picked this number such that the 100 kilometers is on the edge. It's not currently ruled out by some solar system tests. Okay, so moving from lambda 150 kilometers down to 8 kilometers, 8.6 kilometers, I guess, doesn't sound like a big change. You could imagine advanced LIGO making these updates, but that's not actually clear at all, because the actual corrections in the action here, if we go back, you see lambda is just a length scale, 1 over lambda is a length scale. The quartic coefficient, for example, is this to the 6. So it's not at all easy to get down by changing lambda by a bit. It means you change the prefactor here by a lot. So that means you need a much higher precision. And we obtained that you need about 7 orders of magnitude improvement compared to the current LIGO precision. Okay, so this seems quite tough to get there down to there. So is that clear? So there you would be in a regime where at least these scalar models are not are an allowed way of generating Riemann curvature corrections, and the solar system tests can be ignored, but you need to have much higher precision because basically you need the higher order Riemann curvature corrections to be very tiny, but just, with 7 orders of magnitude improvement, that would be the point at which you're just barely measuring them, if you could fantasize that we could do that. And then the scalars and so on that you're integrating out can be rather hidden from us because they only have to generate something relatively small. Okay, but this to me is, a bit negative. I guess I would conclude at this point by this part of the talk. Okay, any questions about that before I move on, or we could discuss again at the end?
Can I ask first, so do I understand correctly that it's all model dependent in the sense that you assume these higher Riemann curvatures to be due to integration out of scalar fields, real scalar fields, and it's not all necessarily the case?
That's right. Yeah, the other cases we could mention extra dimensions, or I think it is model dependent, but I don't think there are too many options to check. So we could, there's not too many ways, I think, to generate higher order Riemann curvature corrections. So it was mentioned earlier, potentially strings, but at a glance, I'd have to think about it a bit more. It sounds like you're dealing with a string length of 100 kilometers, which I'm guessing has various problems to generate it at that level. And extra dimensions at 100 kilometers, I think, I can't imagine that could be possible. So, but again, one could check, but you could see how other possibilities potentially even more obviously ruled out, I would suspect, because I suspect they're ruled out at just simple classical observations. But I could be wrong. I don't know. Does someone else have a thought on that? That would be my gut instinct. But since I haven't thought about the string case much, that's just the first thought I have. At least it's a bit more subtle because it's loop effects that are giving rise to this diagram here. There's an H bar in front. So this is a bit more subtle that this one is ruled out. The adding decoupled scalars sounds a bit easy. Sounds a bit less problematic.
Thanks. Can I ask another question? It's these smaller masses, when you add them, you should have superradiance effect usually. I would expect. So then you can test also with superradiance.
Yeah, that's an interesting point. It could be if we're down at 10⁻12 eV.
It's exactly affecting these kind of 30, 100 solar masses, black holes usually.
That's right. Yeah, it could be. It could potentially do that too. I know that then you might have to think also about, is there some lambda 5/4 term? For us, it doesn't play any role. But if I recall, there's some lambda 5/4 that can potentially shut off superradiance. So we'd have to think a little bit more. But what I've described here, I think, is unavoidable.
Yeah, I see. Thanks.
Okay. So I was just going to mention, although I guess we only have 15 minutes, that the other thing that we worked on that doesn't have these problems of such fantastically low cutoffs on the theory, where you have to worry about all sorts of other things that could go wrong if you introduce new physics at such a low scale. Is there a more kind of optimal approach to have corrections? And this will involve explicitly new degrees of freedom, even in the effective theory. Okay, so the effective theory already has new degrees of freedom. You cannot integrate them out at any level. So it'll be a new degree of freedom that's massless, let's put it that way. This will lead to cutoffs that are still kind of small from a particle physics point of view, but it will not be 10⁻12 eV. It will be significantly better than that. Okay, so that's the sense in which it's more optimal somehow. Okay, so I guess I go through this bit a little more quickly. So this is a variation on a theme that people have played for many years. Probably many of you know. What happens if you add a scalar to Einstein gravity? So here's again the Einstein-Hilbert term. Okay, I didn't bother writing a cosmological constant. It doesn't affect this talk. And then you couple to matter. The Lagrangian for matter is m. and you couple it through some g twiddle, okay, where g twiddle is a function of some scalar phi times g mu nu. Okay, so there's some massless scalar. It's part of the low energy theory. And the only non-trivial thing that, I mean, in the original versions of this, you know, Brands and Dickey and various people played these games. I won't write down their particular action, but the most basic thing you would try is a kinetic term. So here I've written k of x. So x is just shorthand for a half g mu nu d mu phi, so a regular kinetic term for a scalar. And if k of x just equaled x, so there's a function of x, this would be a scalar with a canonical kinetic term, and that's been studied for many, many years, so there's nothing new to say about that. But if we allow for a function of x, things get a little more interesting, as I will describe. Okay, the function, the way you couple is, say we expand around phi is equal to 0, that's fine. And I would just imagine that f of phi is 1. So if f of phi was literally 1, g twiddle would equal g, but there's some correction whose coefficient I call beta. So beta has units of 1 over mass. Okay, if you take the action here and you expand where f like this, so there's an f living inside of the g twiddle here, you expand to leading order, you will find that this scalar couples to the trace of the energy momentum tensor, as is well known. So for anyone who's not familiar with this stuff, this scalar introduced this way is kind of analogous to it's the scalar analog of the graviton. As you all know, the graviton to leading order, or h mu nu, couples to t mu nu at leading order, whilst phi couples to the trace of t mu nu. And if you introduce it in this way, you immediately have like the weak, you still maintain weak equivalence principle and so on. It's put in by hand, right? The graviton has to couple universally. A scalar does not have to couple universally, like the pion and things. So, but the reason this is not so crazy is because people have shown, this is just one paper that carefully considers even these funny kinetic terms, that this universal coupling that you put in by hand is stable under quantum corrections. There's a nice way of showing this in the canonical case. Okay, so that's why it's plausible to imagine. I used to think this scalar stuff was kind of silly, but I got maybe convinced that it's not so silly because, yeah, if you couple it universally by hand, it stays universal to very, very high precision under quantum corrections. Okay. So now the game here, to say something new, is to think about what this kinetic term could be. Okay, so there's some k of x, and you could imagine that this k is, well, naturally it itself has some expansion. So some like effective field theory expansion, it should be powers of x. So x would be just a canonical scalar. And then the higher order terms are suppressed by some scale I call mu. So mu has units of mass to the 4. Okay, and then there's just this prefactor p that looks a little funny to write it like that. I'll explain why I use this 1 minus p later on, but it's not important right now. Okay, so now let me come back to say why I call this more optimal, quote unquote. All right, so the interesting things start happening when you start considering higher order kinetic terms, as we'll discuss. So a higher order kinetic term for a scalar like this x squared, for example, that's something of order d phi to the 4, a derivative of phi to the power of 4. Okay, so you start adding these corrections. Compared to, for example, the Riemann to the 4 that we were discussing throughout this talk up until this point. To leading order, Riemann is 2 derivatives acting on the metric perturbation h mu nu. So Riemann to the 4 is like 2 derivatives acting on h to the 4 with many contractions of indices. And so, and it has to be that way because gravity just forces you to use contractions of Riemann. So you have to have 2 derivatives acting on your field to the 4. But when you start introducing a scalar and introduce non-trivial corrections to the scalar, right? This is like kind of like the analog of the Ricci scalar. Here's the analog, the next correction that's interesting, which is also quartic. You'll notice it has 1 derivative instead of 2. Okay, I could write box phi to the 4, but I don't need to. The most leading order correction is d phi to the 4. So, and if you see that, so this basically has 4 derivatives times 4 copies of the field versus 8 derivatives and 4 copies of the field. So just by staring at this, you can immediately see that these kinds of corrections are going to lead to a theory with a higher cutoff in terms of energy or a smaller cutoff in terms of length than this theory. Because here you're putting up with 8 derivatives instead of only 4. So it will definitely improve the cutoff on the theory. Okay. So let's just get our bearings. If you imagine everything, you're in, say, the solar system where densities are very low. When density is very low, you can asymptotically check that, of course, the kinetic term will be dominated by its leading term because X has units of energy density. And then everything will look very canonical to standard analyses of like quote unquote Brand-Sticky type theories. You can write down the equation of motion for phi, it's some box phi, it's some wave equation with a source provided by the beta, the coupling, and the trace of the energy momentum tensor. If your source is slowly varying, this collapses to the Poisson equation, and the phi for slowly moving things like in the solar system is basically analogous to the Newton potential up to some prefactor. Okay, and famously, it leads to a correction to the metric, for the weak field metric, except this scalar will appear, even though it's numerically related to phi Newton, since it's coupling to t instead of t mu nu, it ends up having a relative sign in the corrections to the metric. Okay. So anyway, this is a standard thing. It alters light bending. Okay, and the bound on that is that the coefficient beta in the Lagrangian, here's the beta, has to be very small, has to be less than about 2.5 times 10 to the minus 3 in units of the reduced Planck mass. Okay, so it's a very tiny coupling. So this already suggests that maybe there is no scalar in the solar system. Well, if there is, it's really tiny. Okay, so I'll talk about this constraint region. Here's the scale mu, which hasn't played any role yet because I just worked the leading order. And then this coupling beta, the strength of the coupling to matter. So it cannot be too big. Now I can just add by way of motivation to put up with such a fantastically tiny beta is that my action, here it is, if you imagine the limit where you send beta to 0, then this term's gone. And then the only appearance of phi anywhere is derivatively. So this theory picks up a shift symmetry in the beta goes to 0 limit. So it's technically natural for beta to be small. So maybe we can tolerate it being a little smaller than 1 over m Planck. Right? The graviton has a shift symmetry to order 1 over m Planck. This scalar has a shift symmetry that somehow has to be a bit less than m Planck. Whether you take that, if you find that satisfying or not, depends on your point of view.
Actually, sorry, Mark, what are the physical consequences of having a shift symmetry in scalar field that is that small?
The physical consequences. Yeah, the physical consequence would be this. It's that the strength with which it couples to matter is extremely tiny.
Mm-hmm.
Okay, so you can hide it as much as you want by making beta so small, right? And the limit is beta goes to 0, and you have the shift symmetry. In this action, it doesn't even talk to matter at all. So it's a completely decoupled scalar. Okay, in terms of direct coupling, because it couples through gravity, but it doesn't couple has any direct coupling. So I don't know if you wanted a more profound answer than that, but does that answer your question or?
Yeah, no, I mean, like, the concept is, well, okay, I see, yeah. Mm-hmm. No, I mean, so the fact that you have a scalar field which have a scaling symmetry, as a shift symmetry.
Approximate, yeah.
Yeah, approximately. Yeah, okay. Yeah, I think it answers my question. Thanks,
Okay.
Mark.
Sure. Okay, and yeah.
So can I ask also a question? Did you try to impose a stronger constraint, or maybe it's already imposed on beta from binary pulsars? Because there is probably, I would expect that there is dipolar radiation on top of gravitational spin-2 radiation caused by this coupling of beta of phi to the stress energy tensor, and maybe this is the way to impose a stronger constraint on beta.
Yeah, so I'll come to a related issue to that shortly.
Sure, sure.
Okay, that's right. Okay, so if you take this beta, so the strength of the force associated with this scalar is proportional to beta squared. So if you square this thing, you're going to get a number around 10 to the minus 5 or so. So just to put this in context, what this beta means would be if you look at the scalar force between two, say the Earth and the Moon, whatever, it is this bound from light bending means that it's weaker than the gravitational force by 10 to the minus 5. So this is a very tiny force in the solar system. Okay, so all right, what do you do with that? You could just say, well, that's that and forget about it. But if we consider this k of x, we say, all right, so I imagine there's an x and then there's an x squared plus dot, dot, dot. So I'll call this the quasi-linear regime where these corrections start to matter a little bit. Okay. So you can have fun taking this action. You can write down, again, if things are slowly varying, slowly moving, the wave equation becomes still some version of the Poisson equation. But when you have a weird kinetic term, you get a nonlinear version of the Poisson equation where this k function appears. Okay, so anyway, this is an equation that you can solve perturbatively. And this term here, the gradient of phi is still proportional to the acceleration that it imparts on a test particle. So that the leading part here is the usual 1 over r squared. And then there's a subleading piece provided by this term. And the subleading piece goes like 1 over r to the 4 with a prefactor that I called r star. So r star is related to the coupling beta and this scale here mu, which sets the strength of this term. So there's some mu to the quarter. And this r star is kind of, I would call it a transition scale. You can see if r gets as small as r star, these higher order terms are really starting to matter a lot. Okay, and then something should happen when r is as small as r star. But when r is much bigger than r star, it's predominantly the usual 1 over r squared force with a correction. And this r star is actually environmental. So it's sort of related to this. It's an analog a little bit of this Weinstein radius, or where the radius depends on the mass of things. Okay, but as we're going to see, this is not the Weinstein mechanism. So anyway, first of all, I should clarify. So should I stop in 2 minutes? We're 2 to 12.
No, not necessarily. You can have like you can have 5. So how long do you need to finish?
I can go through this part quick, but I'll probably need at least another 5 minutes.
Okay, that's fine. Yeah, you can have 5 to 10 minutes. That's okay.
Okay. So what's a little bit interesting is that even when this leading order correction is small, like you're at distances r compared to the transition scale, this new term here leads to precession of the orbit. Okay, and it's precession even if you use this in the Newtonian limit. So you don't worry about corrections from Lorentz, gamma factors or anything. There's still this correction here that survives. So if you compute the correction to precession from some orbiting system, this is the change in the angle of the major axis per cycle. So it's a dimensionless measure of precession. You get this formula here. A is the length of the semi-major axis. And if you compute the ratio of that to the famous correction from general relativity, it's somehow relatively big. Okay, so it's parametrically ordered the ratio of the forces. That's not too surprising, right? And this is a small number, right? It should be 10 to the minus 5, as I said a minute ago. But there's also a factor that goes like 1 over the orbital speed squared, right? Because the GR version is, of course, a relativistic effect. So it's suppressed by velocity squared. But this effect is not suppressed by velocity squared. So this ratio is enhanced by 1 over v squared, the orbital speed. Anyway, you can put this together, and we found in this work that the best bound came from the Hulse-Taylor pulsar, whose precession is measured to fantastic precision. So this is the precession, and the errors are 1 part in a million in the precession per cycle. So this puts bounds then on this theory. There's the parameter beta, which I already said might be around 2.5 times 10 to the minus 5. That's the standard solar system bound. But this scale mu, and recall mu is the thing controlling the size of this leading order higher dimension operator. It puts a bound on that, right? Mu has to be big in some sense. And then the bound is this. And so you wipe out this. This is a region of parameter space that's ruled out. Okay. If you convert this to a scale, so let's say you imagine that the real world is around here at the edge of what we can rule out. This corresponds to, you can say mu to the quarter is something like 200 EV or something. Okay, so this mu, which is a cutoff on the effective theory, is something like nanometers. Okay, you know, to a particle physicist, of course, nanometers is sort of big, but at least we're not talking 100 kilometers, right? This is a cutoff. It's not 100 kilometers. The cutoff on the theory is nanometers, which is still orders of magnitude smaller than the scale over which we've tested gravity. So it's certainly plausible. I mean, it's possible that there is such new physics at a nanometer. We would not know. Okay. I don't have much time, but the slightly more fun thing to think about is what happens in the fully nonlinear regime where you are sensitive to the whole function k of x. So you're sensitive to the plus ... And so you could imagine this sums to something. And let me qualify this by saying, you know, if you imagine you're in a regime where the higher order terms are even perhaps bigger than the leading term, that might sound bad if you're a particle physicist. But I want to say to you that we're not in a regime that would violate unitarity. And the reason is because if we were studying, say, just 2-to-2 scattering, or few 5 particles scattering into a few 5 particles, you can easily check that, yes, you do not want to be in the regime where the higher order terms beat the leading terms. That would be in the regime of unitarity violation. But that's not what we're doing. If you have the sun and the earth and so on, or you on the galactic scale, whatever it is, we'll be talking about neutron stars in a minute, the value of phi is huge because there's a huge source that sets up a large value of phi. But the characteristic scale over which the field is varying is a macroscopic scale, like the size of the neutron star. Okay, so if you apply it, if you have a field thing that's varying on a large scale, that means the characteristic momenta of the quanta is very, very low. It's just that there's a huge number of quanta if you talk in that language. Okay, they're kind of off shell, but there's a huge number of, there's a kind of a large field value. It's a large classical field value. But the momenta are low, so there's no direct trouble with unitarity in this kind of construction. Okay, let me just say a couple of words as to what can motivate certain choices of k, and then I'll have to end. If, depending on choices of k here versus x, you can have different issues with, again, the issue of causality. And again, these are the kind of theories where if you have superluminality, it's asymptotically flat space, you're going to run into problems with causality. So you can check that this k, so k equals x would be a canonical scalar. That's boring, okay? We want to do something beyond that. If it has this shape to it, it leads to perturbations around a background that are subluminal. And if you have perturbations, if it has this shape, the perturbations are superluminal. This is the kind of thing that Mon does. So I'm not going to be doing that. So we're going to stick to this branch, or this class of functions k of x, that at large negative x have the sort of flat. So they have a positive second derivative. Okay. And you can imagine a class of functions that has this property. Okay, so like, for example, if you consider this class that you just make up, it's just the sake of considering a family of models. It's set up so that if p is equal to 1, this is a canonical scalar. If p is equal to a half, this is the dBi action. But if you're somewhere in between, you obey all of these standard properties. Relatedly, in the class of theories that's allowed that gives rise to subluminal perturbations, correspondingly, the force between objects grows faster at small r than 1 over r squared. It grows faster. So that's a kind of interesting thing. The subluminal kinetic terms are the ones that give rise to forces that grow quicker than 1 over r squared. And therefore, you can imagine this physics starts to matter at high densities. Okay, so you can apply these, you can think about corrections in the highest density environments where the force growth is quicker than 1 over r squared. And you can apply it to neutron stars. And I don't have time to go through the details, but let's just look at this. You can compute the correction to the mass radius relation of a neutron star, at least if you assume a simple form for the equation of state. So this dash curve here would be the general relativity result. And this is a new form that you get with certain choices of parameters in the Lagrangian. Okay, these are stable neutron stars, these are unstable. So if you don't want to push the mass radius relation away too much, say a factor of 2 beyond what we've already detected, it puts a bound on the couplings in this theory. Okay, so neutron star stability, as far as I could tell, puts the best bound on these kind of actions. And you rule out some other green region of parameter space. It depends on this exponent p. So for certain exponents, you get up to a bound of mu of like 60 keV. Again, that acts as the kind of honest to goodness cutoff on the theory. So 60 keV is at least a step in the right direction. Okay. I don't have any time, but we did also consider, we were asked about corrections from wave emission. So we computed that as well. And let me just tell you what you get there. The power in the scalar modes relative to the power in GR. Okay, I think this was the question. From 2 orbiting merging objects, at least in the sort of in-spiral phase. The final phase, we don't know. We have not computed because it's too tough at this stage. But the ratio of the power emitted in the scalar mode compared to GR turns out to be order the ratio of the forces times a factor that depends on the velocity, the orbital velocity. And it turns out you get a velocity suppression.
Okay.
So you're already down 10 to the minus 5 because the force has to be small, and then there's an additional suppression. On the other hand, we looked at what is the correction to the tensor power, because the orbit is no longer the same, because there's a scalar force between the objects. So they orbit in a different way, and so they emit different tensorial power. And that one turns out to be, well, it's a precise formula, but that's parametrically avoided just the ratio of the forces. Okay. Oh, I should say, sorry. When I said it's 10 to the minus 5, I misspoke. Sorry. It's 10 to the minus 5 only in the weak field regime. The high density regime, the force becomes relatively big. It grows quicker than 1 over r squared. Okay, so therefore, this is not necessarily 10 to the minus 5. It's bigger. But that's the whole idea. These nonlinear effects give rise to a relatively large force. But anyway, the corrections to the tensor modes, therefore, are surprisingly big. Okay. And so we've left it there. The reason I'm not now going to show you the bound on the parameters from this fact that there's a relatively big correction to the tensor modes, is because our best observations are from merging black holes. And black holes obey a no-hair theorem, so they do not even set up this scalar at all. The best bound from this would come from the merging of neutron stars. And to my knowledge, we only have maybe 2 examples of merging neutron stars. So we haven't had a chance yet to try to look into the data on the merging of the neutron stars, which would set up the scalar between them to see what bound this places. But this is something we would like to do. Okay, so let me conclude. We're saying that introducing new gravitational dynamics is fruitful to provide a guide for existing and upcoming searches in strong gravity regimes. Previous work found that just pure Riemann curvature corrections require a new length scale in gravity less than 150 kilometers. And any UV completions need a mass scale very close to this. New degrees of freedom that generate this, that we considered by integrating our particles, also had a kind of unintended side effect of being ruled out by solar system constraints, unless we have 7 orders of magnitude improvement in precision, which seems kind of tough. On the other hand, we introduce a new scalar force that can lead to a cutoff of order nanometers, for example. And we explain that subluminality has the consequence that the higher dimension operators should lead to a force that grows at short distances, which indicates you should look for corrections to neutron star behavior to look for this. Future work can involve considering bounds from gravitational wave emissions in the neutron star mergers, as I mentioned, and also think about possible corrections in the early universe, as well as UV completions of these kinds of terms with unusual kinetic sectors. Okay, so thank you for your attention.
Okay, thank you, Mark. Questions?
Can I ask, so yeah, as you mentioned, UV completions of quiescence, did you try to do it with just a complex scalar field with some particular potential?
So, okay, a complex scalar field, you mean with the U1 symmetry or no U1?
With if it's pure P of X, shift symmetry, then U1 symmetry, yeah.
No, we have not tried, but that's a good thing to think about.
At least in the cosmological setup, we know that it's possible with a time like X, but maybe in your case, phi is time independent. Maybe it can be a different story.
Yeah, I mean, our phi is well, we want an effective action. If you want this, your effective this is still a Lorentz invariant theory. So, but you're right that you think about loop level in. So do you want to? Let me see if I understand. You have a complex scalar. Oh,
Just without loops, I think just integrating out not integrating out, but even at the classical level, one can reduce it to the k of x.
Yeah. I can imagine doing that with multiple scalars. I'd have to think about doing it with a U1, but with multiples, at least with, yeah, multiple scalars, yeah, maybe like maybe tree level integration out in some sense if one of them was heavy. Yeah, we haven't tried, but it's a good thing to think about. Yeah. We definitely, I don't know, since both of my students graduated, these Jake and Neil, we haven't found enough time to think about UV completions of this. But your idea is something worth thinking about. Thank you.
Okay. Any other questions?
May I just one small just clarification, just to clarify for myself. So in the second part, when you your second part with quiescence, in my opinion, it looked slightly disconnected from the first part in a sense that as far as I know, so this LIGO Virgo bound has nothing to do with the quiescence, which we discuss later. And as far as I know, the numerical relativity for these kind of systems like quiescence, which also have caustic singularities, it's kind of developing science, no?
Right. I mean, yeah, in the second part, as I said, has, first of all, black holes don't even set up a scalar due to a no-hair theorem. So it's relevant to my motivation here insofar as we can do this for neutron stars, or at least we can imagine having neutron stars merging. And when I say we can imagine, we could imagine doing the computation in the merging phase. But yeah, this is numerical relativity at a difficult level. So for us, it was enough to consider like this power output we computed was like in the in spiral phase.
Yeah, okay. Because it's a group like Enrico Barauza and other people who are trying to make, once again, this numerical relativity with quiescence, but I'm not sure if it's.
Well, I guess I wonder what K of X they chose because you mentioned caustics, but I think I would have thought the caustics are precisely in the theories that go like this. But these are, my K of X is a slightly, I would have thought they're free from caustic problems.
Actually, I think there was a paper, if you know Evgeny Babichev, who showed that actually almost everywhere there are acoustic singularities. Essentially, subluminal, superluminal case. So maybe there are a few exceptions like dBi in some certain number of dimensions, which I don't know very well. But acoustics is quite generic problem. And I
Right.
think this is the problem which is manifested when you do numerical relativity, especially. So these high dense regimes, yeah, highly nonlinear regimes.
Right. Well, one thing that may help is that if you have a form that looks like this, which is just a form for convenience, it's not a deep form, but it has it's set up such that when at x goes negative somehow, it enters a new scaling regime, x to the p. So if you enter a new scaling regime, I may be hopeful that one avoids these problems, but I'm not sure. Yeah, it's x in one regime, the boring regime, and then it's x to the p in the other high density regime. And so in that regime, the equations do simplify. So potentially the numerics may simplify as well. But I think these caustics are not a matter of a theoretical obstacle, right? These are a numerical obstacle.
One can show that they theoretically arise. I can say, if you wish, I can send you papers.
No, I'm not saying I meant that they're not a fundamental problem.
I mean, this is kind of something which requires completion, like something which signals that there should be some completion.
Oh, yeah. No, certainly, well, I described it as the theory has at least for me, it has a cutoff of mu to the quarter.
Yeah.
Now, whether it has a lower cutoff than that would be
Yeah.
surprising. But maybe you agree the cutoff is at least just mu to the quarter, and that's okay. Because that's what I admit, it has that cutoff.
Yeah.
But at least for the neutron star regime, typically the scale over which phi will vary would be of order the neutron star itself in the merging phase. So this is, kilometers. And I was putting bounds on mu down to nanometers. So I feel like I can trust this effective theory in that regime.
Yeah.
That's right. Yeah, if mu itself was, or mu to the quarter was, or mu to the minus a quarter was itself order 100 kilometers or 10 kilometers, then I would be very worried about hitting caustics and so on. But since it's at nanometers, I feel like we may be okay.
Yeah. Yeah, as soon as that it's viewed as an effective field theory, of course, there should not be problems.
Yeah. Okay.
Okay. No question once. Going twice. Okay, if there are no further questions, let's thank Mark again.
Thanks.
Okay, thank you.
Yes, thank you for a great talk. Yes, it was it's very interesting, and I hope that we'll see you here again next time. So okay.
Okay, thank you very much.
Goodbye, Mark.
Seeing you.
Bye.
Okay.